So, well, let me introduce Roberto, Anedda, and Elena Curti. I suppose that many of you know them. And you can read the bio, of course, and it is really impressive. We are dealing here with combination of deep expertise in chemistry and in food science. And the title is about how one can investigate an NMR relaxometry, can use an NMR relaxometry to investigate effects of heat treatment in dairy products. And this is a kind of thing that I suppose we are really looking forward, because this is very important application of an NMR relaxometry. So I don't know who of you will start. However, I'm muting my microphone, I'm stopping the video. In this case, please, Roberto, the time is yours.
Yeah, thank you very much, Danuta. And I would like to thank also people from Stellar for inviting us to share our point of view in this very interesting matter of NMR relaxometry. You know, try to outline the webinar, which will be divided in two parts. I will talk in the first part, and first of all, I would like to introduce the problem. Let's say the problem, because still there are several issues that are needed to be addressed by analytical approaches in the dairy sector. And then I will talk about heat treatments in general, which are very important in this producing sector. Few words on the definition and regulations in force. Then I will talk about the effect of heat treatments at molecular level, and especially for dairy products, milk, curds, and cheese. And of course, the possible role and what we have found on the application of NMR relaxometry in this very interesting systems. And then I will talk about a model system that we used in order to optimize our approach, our analytical approach to study these systems, which is called Urasado. Is typical Italian cheese. And then I will talk a few words just to say how NMR relaxometry is now used nowadays in the industry, also not in the food industry, but in the industrial production in general. And I will talk about the main characteristics and some of the applications that are also used for the characterization of different products. In the second part, my colleague, Elena Curti, will talk about experimental data, and will give you some of our experimental results and outputs on these systems. So let's go further. First of all, I would like to say that analysis of milk and dairy products has a long history, of course. However, still dairy producers are facing some relevant problems and issues. I'm just going to list some of the most important here. For example, dairy producers are often struggling with frauds and counterfeited productions. This production pollute the market, especially that of the most requested delicacies, let's say typical and traditional dairy products. Mostly they are cheese, aged cheeses. Moreover, they need to finally check production parameters. Maybe they need to find new ones also. This is what we are proposing today for people involved in the production in the dairy industry. So they need to find new process controls and to optimize cheese making processes. And sometimes they need to standardize as much as possible the quality of the products. Therefore, they need to check the quality features of their products and communicate them to the stakeholders and finally, of course, to the consumers by means of rigorous quality control and quality assurance and assessment processes and protocols. Actually, quality check controls are often carried out in laboratories of the same production plants. For example, many analytical parameters are nowadays routinely and finely controlled in the dairy production. Just to make few examples, I can say, density of milk is controlled, fat content, which makes milk quality, cryoscopy, pH is controlled throughout the production process, acidity, proximate analysis. These are all parameters that are routinely checked. But many frauds, unfortunately, are not detectable by routine methods. And that's why we are talking here today. Another very important issue is traceability of the products, which is in turn strictly related to typical productions, to the territory of production and to traditions. I will spend a few more words on this in the next slides. But now I would like to focus a little more on frauds by citing some of them that have been addressed by NMR relaxometry. As an example, mixing milk from different species and using this milk to produce cheeses that must be produced from a single defined milk sources, according, of course, to the official cheese-making protocols, is not allowed, of course. And adulteration of milk by addition of milk whey is sometimes used to artificially increase milk volume. This is done when milk is sold to the dairy industry, not to get more money, or to increase also cheese yield, because if you add milk whey, you increase the cheese yield. And this is sometimes done by the same manufacturer. Controls are usually carried out on the basis of documents, but sometimes, many times, analytical controls are not usually at I'm sorry, there is a problem with my PC. Sometimes they cannot be controlled for this artificial increase of yield or with addition of milk from different species. Adulteration by addition of milk whey can be detected by using analytical kits. Sometimes some analytical kits are built to verify if whey is added to milk. They check for casein-glycomacropeptide on milk, but unfortunately they only work on bovine milk and do not work when applied to sheep milk, for example, or to other sheep derived from other animals. Heat treatment application to milk is often a relevant step of cheese making process, and it's also very important for milk directed to human nutrition. So milk that is not intended for being transformed to cheese. A problem arises when milk intended for the production of cheeses that, according to the cheese-making protocol, must be produced from raw milk is subjected to thermal treatments. So sometimes thermal treatments are abused in this sense. Also, ripening is a very important step of cheese production. A long and controlled ripening of cheeses confer to the final product's unique characteristics, both in terms of sensorial quality and from the nutritional point of view. In fact, many high-quality cheeses are usually classified and rated according to the ripening time, since it is very well acknowledged that long ripening increases product quality and also price. Many controls on ripening times are based on documents, again, and sometimes they are left to the evaluation of experts that by beating with a hammer and moving the cheese wheels, and by looking at them, classify the products in a somewhat of a rating system that has nothing to do with analytical measurements, but is only based on the human experience. These experts employed in the quality control, for instance, of Parmigiano Reggiano or Grana Padano, are sometimes called, they are called beaters, because they beat the wheels, the cheese wheels. There are no schools or in-depth courses for becoming an expert beater. So the ability of this expert depends only on experience gained in the field. Analytical and objective and rigorous analytical control are of course lacking in this sense, because also this is a very complex system. So it is very difficult to find analytical control that would control the overall quality of these systems. Of course, ripening changes if cheese is made starting from raw or heat-treated milk. In particular, it's seen thermization or pasteurization hinders syneresis of curd, slows down ripening process in some way. And my colleague Elena will show in a few minutes what it was found by field cycling NMR relaxometry. But ripening is greatly influenced by the production chain, by the cheese making process, and by the ripening process too. All these problems finally lead to brand abuse, which is a great damage, especially for protecting designation of origin products. Now, the lack of specific analytical methods able to recognize cheese quality is reflected in many aspects of the world dairy production. In particular, many products are called with the same name, but they are not the same. For example, by looking at USDA official data, the cheese is, as Americans say, Italian type, which is practically the Italian sounding type of products. They outclass American type cheeses. This is very evident in this table. From what emerges from the data, there is no traditional American cheese that can compete with mozzarella for the amount of produced in the USA. You can see here Parmesan is in the second position. Is the production of Parmesan is huge, also compared to many American products. Other cheeses, it is, by the way, it's striking to observe that American Italian sounding constitutes the largest share of the US dairy production sector. You can see here the total of Italian type cheese are usually much more than the American one. Other cheeses varieties are not as much appreciated by American consumers as Italian ones. For example, Swiss varieties show a much lower share of the total cheese produced in the US. It is about 2.5% of the total cheese produced in the US. The lack, you can see here data from 2019, and pretty much the same as in 2018. Italian type varieties of cheese accounted for more than 40% of the total cheese production in the US. Mozzarella makes almost 80% of Italian type products. Most likely this is due to the production of pizza. and other gastronomical preparations. 30% of Italian cheese varieties are produced in Wisconsin. This is pretty curious, right? Especially if we consider that a large share of the real Italian production of some traditional cheese varieties is mostly exported to USA. A typical example is our pecorino type of products, pecorino romano and fiorasado. They are hard sheep milk cheeses produced in Italy, and in particular in Sardinia, where we live, which is the larger producer of sheep milk among Italian regions. This is shown in the graphic. This graphic shows that more than half of produced cheese are exported to US market. This is represented by the green histograms in the graph. By the way, it is worth to note that obviously Italian type cheeses are manufactured without following the restrictive official cheesemaking protocols described in the European Pdo regulations. And this in turn implies that they usually share with real Italian products no more than the name or the brand in case of counterfeited productions. Of course, I'm not saying these are counterfeited productions, but they are imitations, of course, of the most traditional Italian products. The most relevant Italian cheese products, also considering the exported volume, are Parmigiano Reggiano and Grana Padano. They are both produced using raw milk from a specified region of Italy. Still, artisanal tools are used to produce these cheeses, and manufacture is rooted to traditional cheese-making process. There is a strong link between the territory, the terroir, as the French people would say, of production and the quality of the dairy products. This link is acknowledged by European Union, and there is a very detailed regulation on PDO products, protected designation of origins. Consumers buy and eat carefully controlled products for which the whole production chain is controlled very carefully, starting from the raw material, milk, to the distribution, labeling, and the product in the shelves of the supermarkets. Among the carefully controlled parameters are, for example, the animal breeds, the animal breeds, the geographic area of production, animal diet, milk quality, production, storage, packaging, ripening condition, and so on and so forth. Milk microbiota makes quality, of course, and heat treatment, thermization of milk alters microbiota. This is very important, and it has been demonstrated very extensively. For these high quality productions, such as Parmigiano Reggiano, Grana Padano, and Fiorasado cheeses that are produced starting from raw milk, the milk must be raw to preserve all the microbiological richness that comes from the fodder, the cows, the fields, the stables, and so on. The production area gives a microbiological imprint, and each area is unique. That's why these samples, these cheeses, are produced from a specified region in Italy. So this uniqueness is usually transferred to cheese during ripening, and the richness of microbiota modulates the ripening and quality. Another example of this kind is a product that is produced from heat-treated milk, but for which the thermized milk can be used, but not pasteurized milk. This is Pecorino Romano. We will see the difference is related to the effect of heat treatments on milk and cheese which is strictly related to the amount of heat that is transferred to the milk when it is thermized. And this restriction for Pecorino Romano is imposed so as to ensure a given product quality for consumers. Now, heat treatments, some definitions. Thermization is generally used to kill psychotroph microorganisms that are sensitive to high temperature. When microflora is reduced, milk can be and of course the derived dairy products can be safely stored at low temperature for a long time, from few days to weeks or even months. Usually a distinction is made between thermal treatments. Mild thermal treatments are referred to as thermization, and usually with this term are identified heat treatments at temperature in the range between 65 to 68 Celsius degrees, and duration in the range from about 15 to 60 seconds, more or less, in the dairy industry. Pasteurization is usually performed in the high temperature short time processes, HTST, in which milk is heated at 72 Celsius degrees for 15 to 20 seconds. Also, more severe heat treatments are usually performed on milk intended for human consumption, such as UHT treatment, ultra high temperature. This is the most common process in which milk is treated at very high temperature, 120, 140 Celsius degrees for a few seconds. Thermal treatments are particularly important as they preserve milk salubrity by killing pathogens, as we said before. However, thermization causes also many other molecular alterations in milk, and also in milk-derived products and dairy products. Changes may involve to a different extent milk proteins, fat, vitamins. Many vitamins are heat labile. So also other minor components. Those sometimes they are very important, also altered, but they are minor components. For instance, minerals like calcium phosphate, and the main sugar, lactose, which is altered at severe heating conditions. Okay, regulations. Regulation, of course, are what we have in order to control the production, dairy production. According to regulation in force in Europe, milk is considered to be raw if it's not heated above 40 Celsius degrees. Heat treatments involve heating that causes a negative reaction to the phosphatase test. This is what the regulation says. Therefore, according to regulations, heat treatments must be controlled by alkaline phosphatase test. Proof of heat treatment is the inactivation of the ALP, the enzyme ALP. However, this does not have a general validity according to scientific literature. It has been widely demonstrated that ALP test is not suitable for controlling heat treatments in non-bovine milk. Moreover, ALP is a suitable control only if it is applied immediately after heat treatment has been applied, as the regulation said. But okay, so how can we control milk over longer times? How can we control cheese? How can we control mature cheese, ripened cheese? This is, a very important question, because and this question is not answered by the regulations. More than focusing on changes involving one minor component of cheese, we propose a more complete method of analysis, which is based on NMR relaxometry, which is able to describe different effects of the thermal treatments. It is known that thermal treatments have multiple and complex effects on different components of milk. And these effects are somewhat transferred to cheese, to other dairy products, yogurt, ice cream, butter, just to make few examples. Many thermal treatments on milk are in fact exploited in cheese making in order to confer particular and peculiar characteristics to the final products. And that go well beyond the application of heat to kill pathogens. In fact, heat treatments have multiple technological effects too. We aim to provide a new analytical tool to the dairy producers and authorities. In our opinion, NMR relaxometry can be easily exploited to characterize milk as well as cheese, and the effect of heat treatments on the NMR parameters are conserved over time in these systems. I mean, they are not reversible according to our experience, as it was demonstrated in ALP test. The possibility to control metro cheese would open the way to a new quality control plan for the safeguard of typical products. Indeed, to the best of our knowledge, no other analytical method is able to detect milk thermization based on the analysis of cheese. Also, milk quality could, milk quality control would take advantage of new analytical method based on NMR relaxometry. Now, let's go further, and the question is, what are the effects of heat treatments at molecular level in dairy products? To answer this question, first of all, we should recall what structures are present in milk, and then we will talk of how they behave when they are heated to some extent, and how thermization affects these structures. Milk is a very complex system. That's why also NMR relaxometry has been employed not very extensively in these systems. Macro components like fat, water, caseins, whey proteins, lactose, and other components of milk are organized at different levels in milk into supramolecular structures. Proteins, fats, and minerals constitute casein micelles and fat globules, as it is schematically depicted in this slide. Casein micelles are spherical aggregates of casein submicelles, which are shown here, with a diameter in the range from 50 to 500 nanometers, on average 100, 150, 120 nanometers. They are mainly constituted by proteins. If I remember well, about 90 or 95% of the composition of micelles is protein. And colloidal calcium phosphate, which are calcium phosphate clusters, the small black spots in this figure that you can see here, and they stabilize the casein micelles. The mineral equilibrium of calcium phosphate between the solution and the calcium phosphate clusters influences micellar hydration state. Micelles are more or less hydrated, and this hydration is influenced by several parameters. For instance, pH influences this, temperature, like thermal treatment of milk, and in turn, It greatly influences, of course, NMR relaxometry parameters. The interaction between water molecules and other milk components is of great importance in defining the NMR relaxometric results. In solution, beyond water molecules, of course, other proteins are present in milk and milk products. They are soluble whey proteins, mainly constituted by beta-lactoglobulin, which accounts for about 20% of the composition of whey proteins. The four molecular mechanisms that have been characterized in solutions of pure proteins, triglycerides, that do not consider the substructure and the supramolecular structures are not able to precisely describe the whole picture of what happens in real dairy systems. Water is very important in NMR relaxometry of dairy products, as water molecules interact with the protein network and all other molecules in milk dispersions or in the cheese matrix. Also, the size of supramolecular structures such as micelles and globules is very important in defining the dynamical process and therefore NMR relaxation results. This is very important since all dairy systems are dynamic in nature and change with time. Some exchange phenomena are very fast, others take longer times. For example, slow processes occur during cheese manufacture and during storage and ripening. Among these slow processes, we recall curd shrinkage during syneresis, when whey is progressively expelled from the protein network, water evaporation during ripening in aged cheese, while faster processes may involve micelle structure and hydration changes with temperature, with pH, or shifts in the mineral equilibrium with heating temperature, for instance, in thermized milk. For example, it was found by NMR works that with increasing temperature, the solubility of calcium and inorganic phosphate in solution is reduced, leading to precipitation of phosphate and calcium. And dissolution of micellar calcium and phosphate was found to be related also to the relaxation rate of protons, strictly related to the relaxation rate of protons, because it interacts with the casein hydration state. Now, proteins in milk are probably the most affected by heat treatments. This is particularly true when whey proteins, mainly constituted by beta-lactoglobulin, as we said before. However, other minor components like enzymes are inactivated by thermal processes. That's why they have been used as markers of thermization. Sometimes inactivation of some enzymes like lipoproteins, lipase, helps in increasing milk shelf life, but is not detectable by NMR relaxometry. These spot variations are not detectable. Whey proteins represent about 20%, as we said, the proteins in a cow milk. They are globular proteins with a very structured form, and secondary, tertiary structure characterize them. Therefore, they are prone to unfolding and denaturation by heat or other denaturating agents. The first effect of heat on whey protein is monomerization and conformational change of beta-lactoglobulin. Beta-lactoglobulin monomers are present in milk in equilibrium with the dimeric form already above 60 Celsius degrees. Many authors have observed the reversible changes in beta-lactoglobulins. There's a lot of literature on that. At the same time, casein-whey is interested by modification in the hydration level due to changes in the mineral equilibrium. By increasing temperature, the temperature of treatment, b-lactoglobulin undergoes irreversible denaturation and aggregation, which finally leads to the generation of complexes with K-casein. Such changes are known to produce significant modification in milk functionality. That's why it's very difficult to make cheese with severely heated milk. I mean, it's almost impossible with ultra high temperature treated milk, but also with pasteurized milk, it's quite tough. NMR is very useful in describing molecular mobility and system dynamics in general, so can be used in these cases. Many denaturation steps can be followed by NMR relaxometry. Now, NMR relaxation phenomena describe dynamical interaction between the molecules constituting a given system. In NMR relaxometry, mainly two experimental parameters describe the system dynamics, which are T1 and T2. They are called relaxation time constants and derive from the exponential fitting of the NMR signal decay. Fitting can be mono-exponential and give rise to a single peak, as in this graph, or multi-exponential and lead to more than one peak, mainly depending on molecular mobility. As depicted very schematically here, similar to pH, temperature, and other physical-chemical parameters, T1 and T2 are represented by numerical values and describe how protons in the system interact with each other. In this case, we can say the relaxation time T2 of this whole milk sample, which is analyzed here, is 178 milliseconds. Sorry. This animation here, I prepare gives an idea of what is meant when I said molecular mobility. Protons mainly come from water in milk, so signal is very influenced by water mobility. Both water molecules and proteins are free to rotate in solution. The bigger the molecule, the slower it will move. This is described by the correlation time of a molecule, tau c, which can be studied by NMR. This allows to study, for example, proteolysis or protein aggregation or other changes, structural changes that occur in milk during treatments. Water molecules also diffuse through the samples, interact with the soluble proteins. External and internal water molecules exchange with each other very rapidly. D is the diffusion coefficient of water, which explains or gives an idea of this diffusion dynamic. Similarly, water proton exchange with labile protons, and also this exchange is very rapid. It's called chemical exchange and is described by a constant Kx. Close to the protein surface is involved in chemical exchange, and this can be studied by analyzing NMR relaxometry data. This proton population is described by a T2 value and a proton population, which describes each proton environment and how many protons of this type are present in the system. In milk and curd, usually, but not always in real systems, especially in real systems, a single T2 value is observed, and we say the decay is mono-exponential. The condition to observe multi-exponential features, which means more than one T2 value in the system, is the equation that is reported here, where A is the dimension of the inhomogeneity domain. In this case, the micelle radius can be an inhomogeneity domain in milk. It is about 0.1 micrometers, as we said before. D is the diffusion coefficient of water, and delta gamma is the difference between the relaxation rates in the two sites. This means that if heterogeneity domains are large or diffusion is low, we will observe multi-exponential relaxation in presence of the heterogeneous system like cheese, for example. On the contrary, when diffusion is fast, so this is the multi-exponential relaxation. When the diffusion is fast or domains small, NMR relaxometry result will give a weighted average of the state of protons in all possible environments. It implies, for example, that by means of T1, T2, it is possible to investigate on water diffusion, protein aggregation, presence and size of pores, protein hydration, and so on. Mono-exponential decay is due to fast diffusion of water molecules. That we said sample all possible environments or compartments in the NMR time scale. As I showed in the previous slide, whole milk can sometimes show multi-exponential relaxation. It may depend on the method used to fit the decay, the signal decay. Inverse Laplace transformation is usually adopted, but it may depend on milk source, on season. In any case, whole milk can be different from skim milk in the number of proton populations, and NMR relaxometry is able to spot the difference between different samples. This is according to our experience. In curd, signal decay is still mono-exponential. Even when the gel is completely formed, it is mono-exponential. But it becomes multi-exponential when syneresis begins. This is due to separation of water in the whey from the casein network that is shrinking to form the cheese mass. Once syneresis is complete, signal remains multi-exponential and describe the state of water and macromolecules forming the paracasein network in cheese during ripening. My colleague Elena will talk in a little more of what we found when analyzed curd syneresis as a function of heat treatment too. So the non-molecular effects of heat are reflected in some way in the NMR relaxometry parameters of milk. Protein denaturation leads to changes in the distribution of water molecules within the sample. As I said before, this has also important consequences on the functional properties of milk. Retarded clotting time, modification of curd and cheese texture. This is some of the most important consequences. At the same sample, as the sample changes with temperature, we can follow it by monitoring proton NMR relaxation changes. And this is a very rapid measurement, so we can follow online, let's say, the changes that are occurring in the system. Lambelet and co-workers, in their pioneering work in the 90s, showed a steep increase of transverse relaxation rates of milk models as a function of heat treatment from about 60 to about 80 Celsius degrees. The R2, the relaxation rate, which is the inverse of the relaxation time T2 I described before, was shown to be unaffected at lower and higher temperatures, but just this steep increase is, here in this region. Interestingly, these are the temperatures commonly used for heat treatments of milk at industrial level, thermization and pasteurization. I said something before. However, although the work by Lambelet and co-workers suggested a promising application of NMR relaxometry, it did not result in practical application in the daily industry. Likely, drawbacks of these works were the use of long treatment durations. They used 30 minutes heating duration, which are quite far from the generally adopted treatments in the dairy industry. Moreover, they studied model systems, pure protein solutions, sodium caseinate, whey protein isolate, but in order to expand knowledge on these effects of heat treatments, we have analyzed the raw and heat-treated whole milk, curd, and commercial cheeses at different ripening times and from different producers. Okay, after my presentation, Elena will show some results on milk and curds, but I would like to explain our work on mature cheese, and I will be concluding very shortly. This work was made on a typical Sardinian cheese called Urasado. It is a hard cheese and must be produced from raw sheep's milk. Milk from Sarda sheep breed and exclusively produced in the region of Sardinia. So it's very simple model system. This product can be considered a model because heat treatments, thermal treatments are very limited. Milk must be produced from raw milk. Paste is not cooked. The production of Urasado is very simple. It consists of several steps. In the first, milk is heated 34 to 36, 37 Celsius degrees. Then it is curdled using lamb rennet paste. Then the curd is cut and is left to drain. And finally, it is given to the wheels the characteristic shape. And then they are salted for about 48 hours. Maturation consists in the first smoking treatment, about 2 weeks. Then wheels are ripened in cellars. Natural temperature of ripening, 10 to 15 Celsius degrees. And sometimes they are treated in the surface with an emulsion of oil, salt, and vinegar. We have analyzed MRI relaxometry. Many cheeses were analyzed, both obtained for heat-treated milk and their counterparts from raw milk. Analysis have been performed using a high-field instrument, but I believe results are very interesting also for low-field applications. Total experimental time of MRI is about 20 minutes, so it's quite rapid measurement. As I said, magnetization decay in cheese is multi-exponential due to the diffusion regime of water and the chemical exchange phenomena between labeled protein protons and water protons. These graphs are typical T2 distribution obtained by fitting the signal decay. Both types of cheese show two populations. The first due to water protons exchanging with protein protons, which is centered about 8 milliseconds. And this represents the protein hydration water, which is mainly influenced by chemical exchange with protein labile protein protons. And the second population centered about 30 milliseconds, which can be ascribed to the water in a bulk pool. Of course, this is not free to move like bulk water, and this is reflecting the very short relaxation time observed, 30 milliseconds. In heat-treated milk cheeses, the first population accounts for about 80% of the total area, while results are reversed in raw milk cheese, where the first population accounts for only about 40% of the total area. Interestingly, it has nothing to do with total moisture content of the cheeses. And these results show that thermized milk cheese protein hydration is clearly affected by production process. And in particular, it is affected by thermal treatments of milk, since here all other parameters have been fixed in dedicated experiments. So cheeses have been produced ad hoc for these experiments. These results were obtained on cheese after 3 months or 6 months of ripening and appear quite reproducible. We have tested several tens of cheese samples by now, also specifically produced And statistical analysis usually confirm, they confirm that NMR relaxometry is sensitive to these macrostructural changes. It is very interesting that visual examination of the two cheeses show that cheeses from heat-treated milk were characterized by very different appearance than the raw milk cheeses. Heat-treated cheeses are more homogeneous. They have a scarce amount of pores, and the paste is smoother. Upon cutting the heat-treated cheese, milk cheeses, the cheese were cut very easily with straight lines. On the contrary, raw milk cheese has a grainy paste and a friable, brittle paste, and heterogeneous with larger eyes and slits, and so it's very different also from the visual. But you know, we cannot compare visual appearance if we don't have some number on more rigorous analytical approaches that would validate the visual appearance, the evaluation of visual appearance. The exploitation of NMR relaxometry, and I finish with, has several advantages over other techniques. The most relevant are that no sample preparation is required. The measurement procedures are simple and fast. Instruments are very stable, and you know, with permanent magnet technology, the popularity of this kind of experiments have grown in popularity. There is no need of over-specialized personnel. Of course, given suitable user-friendly software or interface are optimized for specific applications. Routine maintenance, especially for fixed field benchtop and instruments, is very easy and quite inexpensive. Benchtop NMR instruments are relatively cheap, heavy duty, small, and can be easily implemented in small laboratories. Fast field cycling NMR share most of the TD NMR benefits. In addition, it has an important advantage over fixed field instruments because it can probe a range of fields. It allows investigating both very slow and fast molecular motions. Several TD NMR applications and also the NMR relaxometry application are already exploited in the industrial quality control assurance applications. For example, in food industry, solid fat content is applied in the oil confectionery industry, which is an official method. Proximate analysis can be carried out quite easily in the and the spin finish in the textile industry is very much used for which previously solvent extraction was needed. And now I'd like to hand over to my colleague. I'm sorry if I stayed a few more minutes than expected. And thank you, of course, for
Roberto, thank you very much. I suppose that the best idea is to discuss the subject after the next part.
Yes.
Do you agree?
Yes, of course. Thank you.
Okay.
Okay.
So I'm gone again.
Yeah. I will share screen. Just tell me if everyone. Can you see something?
Yes.
Okay. Okay.
Yes.
Okay. Good afternoon, everyone. So as Dr. Anedda was saying, I will show you some practical application we carried out here on milk and cheese. The first study I would like to show you is about a very extensive screening performed on ewe milk during a very large period of lactation. It was, if I remember well, from February through June. So we choose to to have milk that was daily provided and was obtained by a single flock, so that we can exclude any variability due to the feeding on the flocks and the location on the flock itself. So we basically get a daily milk supply from a flock, and from the supply we managed to produce daily from 3 to 6 batches, and from each we produce 3 samples. Okay, so one sample was raw samples, raw milk without any further treatment, and 2 samples were heat treated for 2 different times, 15 and 20 seconds. I will call this sample R, HT15 and HT20, and see here. So, the entire time of these studies, we collect almost 1,100 samples. So I think this is a pretty large number, because we collect them, so we able to collect these data. So all the samples were analyzed with the low field TDMR from Booker that rates at 20 megahertz, and the analysis was carried out at 25 degrees Celsius. So we basically measured both T1 and T2, and we processed data, and as Roberto before, we obtain the distributed relaxation times, from which we extrapolate the characteristic times that corresponding to the maximum height of the peaks. So we get a mono-exponential behavior in T1 and a b-exponential behavior in T2 as the second population, so the were mobile, can be likely attributed to fat, as we proved in other experiments. And first, relate to all the protons that are interacting in the domains where soluble proteins and water are present. So if we take a look at these characteristic times and to the distributions, observed is that in all the heat samples, we observed a shift of the distribution toward left, so the characteristic relaxation times became shorter. And we also performed some statistics because we want to understand if this shift considered in some way significantly relatable to the fact that milk was subjected to heat treatment. And what we saw is that T1 showed no significant differences, but T2, on the other hand, indicated a significant difference, both for the sample treated 15, but also for the samples treated for 20 seconds. And this difference was proportional to the duration of the treatment. So from this data, we could surely say that the NMR was able to spot the changes in the molecular dynamics of milk when it's when milk is heat treated. Okay, so and the changes of T2 were also related to the heat treatment durations. From previous works that were published on how whey proteins modification are relatable to the heat treatment, we hypothesized that this T2 shift could be in fact related to some changes occurring in whey proteins, and also to possible interactions of whey proteins with fat globules in milk. Okay, so if we look to the following steps to which milk can be subjected to produce cheese, we can also monitor with the NMR the process of syneresis, as was saying Roberto before. So we select this time 2 types of milks from cow and goat, and in the same way we did from the previous study, we use both raw and heat-treated milk, again at 72. So we put the milk in the NMR tube, and we decided to add rennet for curd formation directly in the tube. So we can observe in the TD-NMR the developing of syneresis. And we measure T2 over syneresis. So from time 0, so when we just add the rennet, and every 10 minutes from the cutting operation until 70 minutes after syneresis. So what we observed at time 0, so before we add the rennet, it was the presence of a main population that we call population P, that can again be attributed to the protons that are interacting in the protein-water domains. But if we observe in both milks what happens after 70 minutes from the rennet addition, we could observe the appearance of this population that we call population S, that is represented by a T2 that is pretty similar to the T2 of bulk water. And that's because this population can be reasonably attributed to the way that is actually expulsed from the curd over syneresis. If we go back to what happened when we heat-treated milk, well, in this study we could see that there was a difference in how T2 relaxation changes over syneresis, because if when we looked at the data, both to the percentage of population P and to the relaxation time T2P and to population S as well, we saw that in the heat-treated samples we have higher values of population P and smaller values of population S. And we also observed that during syneresis, population S is increasing in percentage. Okay, so we could hypothesize that the fact that milk was heat-treated also affected how whey was expelled from the curd. And in the case of the heat-treated curds, we could say that we had a higher retention of whey that was relatable to the fact that proteins were actually modified by the application of the heat treatment. So at last, I would like to show you the data that Roberto was talking before. So we are in Sardinia, so we choose one of the most ancient and cheese that are produced here. That is actually a Pdo cheese. So it is a very peculiar product, and it follows a very strict protocol of production. So as Roberto was saying before, it has a very firm and crumbly paste and a very piquant flavor. However, if we go to any supermarket here, you can see that the market offer includes very different products. So if you just look at these cheeses, you can see, if you can see the pictures, they are very different because you can find also products that showed a very smooth paste and did not have any of the features that the Urasado should have. That's because the market supply is mainly from the dairy industry. Okay, so these products are likely to be to be put in the market by big dairy factories. So we would like to see if NMR techniques were able to discriminate in some way these products, as there is no method right now that is able to do this on final products on cheese. So we went to the supermarket and we actually bought both industrial and artisanal Urasado cheeses on the local market. And we perform both low resolution NMR at 20 megahertz, and we use also a fast phase cycling NMR spectrometers, so that we could observe a much larger window of molecular mobility in these samples. So if we look at the TD-NMR results, again, we can see a mono-exponential behavior for cheese as regards T1. But in cheese, as was saying Roberto before, we observed a multi-exponential behavior. So here we see 4 peaks. For this study, consider all the first one because it was the most consistent in all the data we collected. With to this time to compare the samples. What we was that all the industrial samples had higher values of both T1 and T2. So you can hear the red columns. Okay, so we could say that industrial samples showed a higher degree of T1 and T2 mobility. Look at the fast field cycling results. I put here a graph, and frequency is plotting against the relaxation rate that is the inverse of T1. So if we look closer to these lines, we can see the industrial samples have a much lower relaxation rate in comparison to the artisanal samples. Okay, so they have a lower relaxation rate and a higher T1. Okay, we were able to hit this curve that can actually fit with the different mathematical models. We choose a mathematical model that was able to give us answers that could in some way describe how the casein network was influenced by the processing of this sample. So here I summarize that we obtain mainly parameters that are called B and F. I will not go into much detail. They are they can describe the microstructure and the degree of hydration in the casein network. So if we look at the values of B and F for the industrial cases, we can see these samples have lower B values and higher values. So from definition of parameter, we conclude that in the industrial samples, we have a higher hydrated casein network, and that we also concluded that more proteins were retained during syneresis, as we saw before in the study of, about the curds. Okay, so we can also say that FFC's results confirm what we observed with the NMR. Again, I would like to highlight that what Roberto was saying before. So if we look at the structure, at what we see when we open a cheese and what the cheese is, that these groups of cheese is different. So again, the artisanal cells are very crumbly and they don't cut easily, while the industrial ones, they give more precise slices and they more easily cut. So we can say that what we saw at what we observe both NMR and FMC can be reasonably related to what we see at when we look at cheese. Okay, so that is the result of all the steps that are made during the processing of milk to cheese. Okay, so our conclusion was that if industrial samples showed these features, so in summary, we can say that they had a more hydrated molecular structure. We can say that these features can in some way related to baking process. Okay, that in dairy industries involve a more controlled processing, so that this is very different from what the shepherd does when he produces an artisanal Urasado cheese. Okay, I mean, we can more mechanize the operation, and of course we get more uniform production that have in some way lost their peculiarity. And of course, we could not exclude that in such productions, maybe heat treatment was applied to the cheese, and that this application was reflected, okay, in the final cheese features. Okay, I'm done. So thank you very much for your attention.